want to be thoughtful about, okay? And not a lot of things like this were dismissed out of hand early on when people weren't used to or comfortable with dealing with them, and today are considered very serious political, social issues. So not to be easily dismissed, even if you disagree. So I just wanted to say that. I didn't mean to be flip about it, and I want to thank you and anyone who brings that up. I think that takes some courage, and I think it's the right thing to do, and we all benefit. So I really just wanted to not give the impression that I had been dismissed. So you want to say something about that? It's nothing.
Thanks.
Okay. So let's talk about operating systems. Okay, so before I start with this, I will say there was it was a point I quickly saw where people came and spoke to me. There was a problem with the grading on problem 5B in particular. Okay, so if you disagree with that, you don't have to run telling me. I know. Okay, that was a miscommunication between me and the PAs there. Okay, and what I'm going to do is at the end of class, if that's the only problem you have, if you should have got, I'm not going to take away anything. If you think you should have gotten those points in particular, I'll take the papers back in. I'm going to look at them and do myself, make sure they're correct. And you don't have to bother coming in and talking to me or anything. Okay? So if you have that issue and other issues, then come to me in office. Okay? And I apologize for that miscommunication so let's talk about the rest of it. Okay, so the difference in context switching, of how the context switch is implemented between threads, okay, in something that is implemented completely in user mode versus threads that are implemented by the kernel, right? So this is the difference between a many-to-one model and one-to-one model in terms of the book. So in both cases, in every case with context switching, we have a context which is certain register values, in the case of kernel mode, all of the user accessible registers, okay, you can list those, but the important thing is they have to be the user listed accessible registers are written into program memory in some buffer. It's the only place the user really can write it. Okay? And then those values of those registers are taken from an existing buffer and loaded into the user register. That's user mode. In kernel mode, we have a task control block in the kernel, and in order to make a context switch, the values of the user registers and the architecturally protected registers, in particular the PSR and or the other registers that implement the virtual memory view, are written to the task control block, and those values are taken from another task control block of a running process and written into the user and protected registers. What happens when a user thread a thread gets implemented completely user mode thread to read from a pipe. The entire process blocks. None of the threads in that process run. Nothing runs in that process. More about threads. What about multiple stacks? Why is it unsafe? It's unsafe because when you have a task control block, you can use the virtual memory mechanism. I'm not saying what it is. You can use the virtual memory mechanism to put the stack in its own segment, and when it overflows, you get an error. If you're doing user level threads, the stacks go into a data structure in the heap, or perhaps in the statically allocated data area. Either way, there is no protection for stack overflow. Okay? So if you overload the stack, you're going to keep going into adjacent data structures of stacks. Yes?
On systems that use paging, can't that be averted by having using mmap or something like that to explicitly allocate a guard page at the end of each user allocated stack?
Essentially, what you're saying is if you have a mechanism for using virtual memory, so you could make that argument if you had a bunch of machinery we haven't discussed yet. Some of it I don't know the details of, but I would be willing to admit the possibility. And if you wanted to give that answer, you'd have to make that argument. I would evaluate that. It's not out of the question. You'd have to use, I mean, there are things, I will admit this, operating systems have all kinds of features that we haven't covered. People add them in, and sometimes they make user level more powerful in ways that I don't even know about. Okay, so I did say just said what makes it unsafe. Again, I'm open to such a discussion if that was what you were thinking. The implementation of the heap. What's up with the implementation of the heap? The heap is a shared data structure. Right? The heap is a data structure shared among the stacks. It's got pointers and other structures that are changed and shared by multiple stacks. If multiple processes try to modify the heap by allocating memory, modifies the heap, you're going to have race conditions here. Semaphore. Okay. So part 3A is in the book. So you can look it up there. That's just the standard implementation there. And why are two semaphores needed? Two semaphores are needed because a semaphore can only block on one condition. When it's 0, and there's an attempt to allocate beyond 0. Okay? A bounded buffer needs to block on two different conditions. It's empty or it is full. One semaphore can't detect both of these. So you need one semaphore to detect if it's empty, and one semaphore to detect if it's full. Reader writer locks. I don't have the code for this written out here. So it's very simple. This is how it's phrased. You want something which is just like a reader writer lock, but limits the number of simultaneous readers to no more than 10 at a time. Okay? So how do we do this? Well, we use a semaphore that we initialize to 10. That's a good start. Okay? And then we want to know when do we wait on that semaphore and when do we release that semaphore. And we wait on it after we acquire the read-write lock. Okay? And we signal it before we check and release the read-write lock. So the reason we do it that way is if you did it before you acquire the read-write lock, then at the end of the first 10, when the count got to 0, you would allow writers in at that point. Doing it this way means that actually you want it, to think about it off the top of my head. You want it inside the read-write lock so that you allow people in and then they go through 10 at a time. So it's got the same structure, but you have a semaphore inside the read-write lock. I'll put that up on the actual code, so that's clear. Another point, actually, technically, which I did not take any points from, you should change the read-write lock code to use a different mutex for making the you don't want to have blockage between the entry and exit segments. So that basically get a semaphore 10, put one in the entry points and one in the exit point. That's almost all points. Exactly where you get those semaphore wait and signal placed is just the last few points, the last bit points. I will put the solution up for that, so that's one pseudocode. I don't have it written out. And the CPU scheduling algorithms. So this is if you have shortest job first, you can have preemption. And I'm sorry, you can have starvation since you can keep feeding in short jobs, keep a long job out. B should also be yes.
You can't see for, can you scroll?
Sorry?
Can you scroll up?
Oh, I'm sorry. Round robin cannot get starvation because once you get in the queue, you're going to go to the front of the queue after the ones in front of you are done. Priority without aging, yes. You can get starvation again by having higher priority jobs until you come in and keep out one. And first come, first serve, no, because like round robin, you're going to get to the front of the queue. The only difference between those two is round robin, you don't get to finish all at once. You have to go around and know how many times it takes. First come, first serve. When you get to the end of the queue, you're going to run to completion. Some people, I forgot to put this in as a proviso. What about a job that loops infinitely? If a job loops infinitely, scheduling of these types just doesn't work without some kind of a time limit that kicks you out. We didn't really talk about these algorithms in that context because we're talking about them in the abstract. If someone gave the answer, meaning yes, there could be infinite looping, and you said so, then we gave you the points. That was your assumption. Okay? There's some unstated assumption in general, and you want to use that assumption, and you're not sure, you can ask in class or you can write it down on the paper. But if you just give an answer that makes an assumption that wasn't stated and is in your head, that's a problem for grading. So that's that. Sorry? The process.
Also, the process not get blocked with first come, first serve.
First come, first serve. No, because whatever is in front of you on the queue, all of those will eventually run. Right? I mean, the first one will run, it'll be done, it'll go away. Second one will, no one can get in front of you in the queue with first come, first serve. So, however long each of those things take, you will, every process will eventually run. Does that make sense? See, whereas with, say, priority, if you're a lower priority process, you get in front of I mean, if you're a higher priority process, you get in front of the lower priority process. So you can keep that lower priority process from getting to the head of the queue. But with first come, first serve, it just goes by the order in which they arrive. That's the only consideration. Okay. If you have more questions, come by. That's okay. So that's the overall thing. Just hopefully give you enough if you think that there was a mistake or you have an argument with any of that. 5B, just come and give me your paper. Okay. And I'm going to be, I apologize for that. That's at the end of class. Okay, there is more homework up on the sort of had a hiatus in homework because of the exam. So I put two homework assignments for chapter 7 and chapter 8 all due together. So it's kind of a catch up thing. We have a week to do that, and hopefully everything also up on Blackboard is done without anyone reminding me. So, and someone had asked a question, which I've also been thinking about, particularly in the light of having to do this discrete rating, about the final. Now, last year, I actually did all the grading myself, and I'll tell you, it was painful. It really was. I had the same kind of size classes, 5 questions per student, 150 papers, in the 2 classes, 750 questions. So but it is important, clearly, we have no time for regrades after the final, or almost no time. It's very difficult to deal with that. So I'm gonna try to put extra efforts into being involved. I won't quite promise to do all the grading myself. I have to figure out if I'm really up to that. But at least I will be very much involved there to give try to give the equivalent of some kind of review and to get what you would get out of the opportunity for a grade. Because, especially the way this grading, this course goes to final is, for many people, really central. And so I hadn't quite figured that out yet. I may just like the both and do it just because then simple, but it's a little pain. So I'll let you know close to the time what I figured out. But if you're concerned, put it that way, about that issue, it is being addressed, and try to make sure that post final grade is accurate as much as possible. Okay. So we got to the paging here, how page tables are implemented, and we got as far as TLBs, remember, translation look-aside buffers, and so translation look-aside buffers, just give a little anecdote. People were asking essentially at one point, what about, it was actually during the review, when it was not the time I really wanted to talk about it, or it was at some point. What about essentially extra architectural hardware contexts? And it is true, if you have more hardware contexts lying around in your machine, you can do switching faster, lower overhead, and you don't have to pay as much for writing all those registers out to memory, even fast memory, loading them into memory. And that is an approach that people have taken to try to speed up the execution of multi-threaded machines. Okay, so the way we've been learning about processes and now threads, processes are pretty important. They come in pretty quickly at the beginning because you need to share a machine. So it's a form of sharing a machine. Threads come in as a way of programming, and they're more than sharing a machine. A single programmer, a single process has associated a set of threads because you want to express concurrency. And if you have multiple processors, you can actually get parallelism. And it turns out, even if you don't have multiple processors, you can get good pipelining effects by having threads, by having concurrency, because you can get multiple threads to share a pipeline more effectively than instructions in a single process can, because multiple threads are more independent. They're independent of one another. So we've gone from processes that were like about sharing the machine, sort of virtual machines early on, threads more a way of programming, and today a way of now using multi-core. You actually have multiple pipelines. Threads allow you to do that, and you can see if you have multiple cores, you can run multiple threads with zero overhead because you run them all at once. You don't have to switch at all. So you're going from a situation where you had more than one processor thread, you always had to pay an overhead. Now, if you're using the multiple contexts, the pipeline, but also the register sets there, okay, because they are multiple, you can assign one per running core, and you can keep them all actually in that context. And if you had actually more contexts, more cores, think about this. What if you had more cores than you had runnable threads? Not that hard to imagine. The Cell processor from Sony had 8 cores. Okay? There are people making processors with large numbers of cores, generally special purpose kinds of processors. GPUs are highly parallel machines also, but those are special purpose. But if you had more threads than cores, you could leave a non-running thread in the hardware context. Just leave the values there. You wouldn't have to write them to the TLV, right? And then you would have no cost for context switching, for moving stuff back and forth from that. So there is this idea, yes, if you have more context, you reduce the cost of switching, but you just have to, first of all, someone has to put the hardware into that. And then secondly, someone's got to manage that. Okay, so does anyone do this kind of thing? Yes. People have architectures that, for instance, have, I mentioned time, one set of registers for user mode, one set for kernel mode. So now when you go from user mode to kernel mode, say on a clock tick, you got the registers all loaded, you don't have to do anything except change the bit in the PSR, and that means you're running using the kernel context instead of the user context. So that very much cuts down on the overhead you take on every clock tick. Why don't you always do that? Clock tick overhead is not necessarily the most burning issue in the performance of processors, but it's something that has been done. Okay? And the same thing helps on every single system call. You pay a lower overhead because you have a hardware context for the user, and for the kernel, it's just when you switch users, you have to make that choice. How about if you had multiple sets of user? Well, we said multiple cores. You have a set of registers at the user level. we had a large number of contexts you could implement contexts, sets of registers at the user level, even more than you have cores. And if you did that, it would be just like a hardware adjunct to the TCB, right? Instead of writing everything to the TCB, you could leave it in a hardware context and just, when it becomes runnable, just give it a core. People have built machines like that, okay? There was a machine, so this is just, again, just an aside, but while we were building machines of the kind that we've been talking about, to the extent that we talk about architecture in this course, which come from the single-threaded, single-core machine, which was standard in, say, the 70s, people have also been building machines that are designed to express concurrency through large numbers of threads. Even before they had parallel implementations, multiple cores, the idea was that would enable you to run a whole bunch of threads without any overhead switching between them. Because you would keep multiple contexts in hardware. There was another machine designed, or first one I know like this, had 128 register sets for one processor, one core, but you could keep the register sets for 128 threads in memory and switch between them at no cost. All you had to do was the hardware had to decide which one to run at any moment. And so that enabled actually the processor to switch between threads instantaneously. So that was a more parallel kind of machine, but it still only had one pipeline. That was designed by a man named Burton Smith, kind of a visionary in these kinds of multi-threaded architectures. He founded a company called Terra. These kinds of companies are pretty much funded by the government, by the Defense Department, to try to keep up with. The problem is they don't want to fall behind. If architectural approaches change suddenly, and multi-threaded architectures are the only way to get more performance, in the meantime, if we stop designing those machines, because all the fastest machines are much more conventional, single-threaded or small number of threads and cores. The issue is then, well, we don't even make those machines anymore. Not only we may design them, but they're made abroad. And that's why the Defense Department is concerned about it. They're concerned that if we sort of get complacent about architecture getting too static, then we'll be stuck. We'll have to do new things and we won't have that capacity. So they fund these small companies. Multi-threaded architecture was one of the things, the Terra computer, and it was sold to supercomputer centers and to the military. It never sold a lot. But that company was successful enough to take over Cray Research when it failed. Cray Research being in the business of parallel computers, and being founded by one of the pioneers of computer architecture back in the 60s, Seymour Cray. And they bought Cray Research. They took the name Cray Research, and so that company is, if you know, the Cray machines at Oak Ridge, those are the biggest supercomputers pretty much in the world. It's actually that same company. So it's a parent. What happened to the MTA, multi-threaded architecture? But they kept making it in bigger and forms, thousands of hardware contexts in a parallel implementation, but it never won. It never eventually, I think Cray stopped that altogether. But it's always been out there and it always comes back. Why? Because as the machine gets bigger, you have more and more need for parallelism. even just parallelism in accessing memory to cover up the latencies of accessing memory. And so that's you ask the question, could we add more context? Would it speed things up? The answer is yes. To a certain extent, we do that, like adding cores, but architectures that go overboard, adding a lot of context, so far have not been winners, but that's not to say they won't be in the future. Hyperthreading. So hyperthreading puts multiple threads on the single pipeline. Right? So when I say if you have multiple threads, you can even use a single pipeline better, that's hyperthreading. Okay? So yeah, that's another dimension. That's these machines that have lots and lots of hardware context, they can use hyperthreading because you need to. I mean, hyperthreading, you're taking turns executing instructions from two different threads. You need to have both of those contexts loaded in. So when we talk about caches, same thing. There are architectures that have partition caches so that you don't have to flush a cache every time you do a context switch. So some architectures, just one big monolithic cache or shared cache that multiple processes can use without getting in each other's way except competing for the space, or partition caches, which are more like separate contexts. People are playing around with these things all the time. There are multiple conferences. Architectural support for operating systems and programming languages is one of them. A very distinguished conference, going on a long time. People run endless benchmarks with different simulated architectures and try to prove one thing or another is better in terms of an approach. A lot of people feel it's gotten to a point of diminishing returns. But, I don't know, people still do research in it, and it's still some people's careers to try to figure out, because all of the speeds and sizes of things change over time, depending on technology. Yes.
Do you have an idea like how much parallelism is happening with today's operating system, consumer operating system?
How much parallelism in the operating system?
Like for the multi-core normal desktop.
Well, so the Linux kernel is multi-threaded, so you can have multiple threads running in kernel mode. And I think almost all the functions are parallel. That is, they don't. The alternative is to have one thread that essentially locks parts of the kernel and is the only one that can do it. I believe the Linux kernel is pretty much completely parallelized, so you do synchronization among threads that are in kernel mode. And so you can get as much parallelism as you have cores. But there's, of course, if you have synchronization points, like you have critical sections, then that reduces it. So it depends. If everyone's working in the file system on the same files, there's less parallelism. One person is working in the file system, another person is working in the network, then both of those kernels those parts of those kernel threads can run at the same time.
Yeah, thank you.
So early on, when people started with multi-core, the thing that was generally done was just to say one thread at a time can be a kernel mode running, because that's easy. But that also restricts the amount of work the kernel can do. So now modern operating systems are fully parallel according to up to the number of threads of cores. So you can imagine, those of you who've done 360, you've done a heap, you've done malloc. So imagine writing a heap that's parallel and used by multiple threads. You know the synchronization primitives, you've got mutexes, you've got semaphores. So, you can have some ideas. It's not a trivial matter to write a heap that works well and is shared as a data structure, let alone all the other things that the kernel does. Okay. Oh, so there's the DLB picture. I was going to tell you the last part of my anecdote. Didn't get to the last part of my anecdote. When I was Working at Bell Laboratories, they gave us a machine, which actually had been a copy of a commercial machine. They used it for electronic switching, but then they decided they wanted to sell it as a computer. It was back when AT&T was going through its breakup and didn't know whether it wanted to be a computer company or a phone company, go out of business. So they said, you have to use this machine. It was, and this machine was interesting. We put our operating system on it that we were working on. And this machine had an unusual feature. It had 8 TLBs. 8, so this is why it's a good example. Say, can you do more hardware context? Yes. You can do 8 TLBs easily. You could back then. So a TLB is a kind of cache. So if you don't have multiple TLBs, then every time you switch between user processes, you've got to flush that so it can be filled up with page table entries from the new process, right? Otherwise, it's going to have invalid data. And as it turned out, Unix, the way it was written, had been ported to this machine, used only 2 TLBs, user mode and kernel mode, two memory views. So you could switch between user and kernel without flushing the TLB. But if you switch between user processes, you would have to flush it. So that flushing it means, actually, since it's read-only cache, you don't change the page tables while it's operating. So it just means getting rid of those entries, but then they have to be read back out of memory. So I had a little time on my hands, and I learned about algorithms for sharing memory and context. So I said, I'm going to write an algorithm that will allow all those TLBs to be used. So you can have up to 8 contexts in use. You only have to flush them when you get to a 9th that wants to come in, and you got to flush one of them out. And we'll do some algorithm to choose which one to take out. Policy, standard policy, I shouldn't talk about it. Second chance policy, doesn't matter which one it is. And spent some time doing that, got it to work, ran some benchmarks. It was this operating system that did message passing, and there was no change in performance. Zero. I could not, the only way I could get any changes to have 2 processes that just sent messages back and forth to each other. So basically, they were just doing context switch all the time. Then I could get a measurable difference in performance. Other than that, nothing. So the answer is yes. I guess that explains why they were not using all 8. I don't know why they put them in. Probably someone who was designing the machine said, yeah, sure, let's put in more context. Let's put in more TLBs. Sounds good. And then it turns out it doesn't really give you better performance. So it's, you can't assume that that's going to happen. So you can compute an effective access time, and all it is you look at the access time if you have a hit, okay, which is going to be fast, and that has to be given to you. You can't calculate that. And you look at the access time if there's a miss, which is going to be a function of the memory access time, okay, depending on what you have to get from memory. In this case, the page table entry, just one word, and you multiply the probability of a hit by the cost of the hit, multiply the probability of a miss by the cost of a miss, and add them together gives you the expected, or they call it effective access. Okay, so that's basic probability. I'm not going to make you calculate that because it's not really an important skill, but the idea is important. It's just basic. It's basic probability. You got the probability of one event, probability of the other event, and how you combine those. Okay, just multiply each one. I'm not going to go into the details. What it tells you, if you do all that, is you've got to have really high hit rates. Okay, hit ratio often greater than 99% in order to make that work. The because this is now TLB is being on every single memory access, right? So I'm not going to dwell on that. It is important that you know that if your hit rate is not really, really high, you're going to kill your performance. That's true on the data cache, it's true on the TLB, and actually the coding. It's true on the general memory cache, it's true on the TLB. The TLB, because it's so focused, the page table, you can expect, you get a very high hit rate. Memory protection now this is, in some sense you could say, okay, you're saying that paging is so powerful, what's so great about it? It's a lot like segmentation with fixed size and smaller units of memory than segmentation had. What are we so excited about? What does paging allow us to do? And here's the thing. So first of all, the fact that pages are small enables us to do very fine-grained policies based on per page. And the other thing we have then is per page valid, invalid bits, okay? And memory protection bits. So memory protection is this a writable page of memory? Can you do a write into it? Or is it read-only? It's a big deal, the ability to do that. Valid, invalid says, is there actually memory at all? Is there any physical memory associated with a particular page number? Why wouldn't there be? Well, remember swapping? We took a whole process, moved it out to disk, and there was no memory there for that. We couldn't run it. Here we can do the equivalent thing on a per page basis. And if we write out the contents of a frame associated with a page, write it to disk, and mark that page as invalid, then there is no memory there. There is no memory there, physical memory to access. So valid means there's something there. It could be read-only. So we need multiple bits to express all of this. Invalid means no, there's nothing there. But it doesn't just mean there's nothing there. It means nothing there, and we're going to trap to the kernel. We're going to give you a trap. Equivalent, what else is a trap? Divide by 0 traps you to the kernel. Any invalid address access that doesn't correspond to a location even is traps to the kernel. It means any read or write, even though the program is not making a system call, there is no clock tick. The read or write operation can end up being fielded by the kernel because it was to a location where the page was invalid. Why would that matter? It means we can do things with what's in memory. The kernel can implement services based on the fact that some of those pages are invalid, and when someone tries to access them, then a service will be performed. So we're about done. Give you the very simplest service, just so you have a concrete example. We'll come back to a more complex example. What if you had a big, big area of memory that you wanted to be filled with zeros? Normally, without access to something like this, you'd have to allocate the memory, all of it, fill it with zeros, then you could let the process run. But if instead you just mark all those pages invalid, then when someone tries to read one of them, or let's just not look at right yet, tries to read one of them, the kernel is entered, it says, oh, this is one of these pages that is virtual zeros. I'm going to allocate a page, a frame now, from a physical frame, fill it with zeros, put it in the page table, mark it valid, and restart that instruction. And now the read restarts, reads the 0, and it's empty. So you can have an area of memory, maybe even much larger than the physical memory of the whole computer, which if a process tries to read anywhere in that area, it's going to get 0. But you didn't have to allocate the memory. You didn't have to fill it with 0. It's virtual. So that's perhaps the simplest service you can think of. We'll talk about more complex and more complex services.